that we're going to talk about today. The first is kind of a big one, which is the idea of a struct. Okay, so a struct is a compound data object that you can create that has sort of within it other data objects. Okay, so if you wanted to have, for example, a program that dealt with like a list of customer records or something, right, then the structure or struct would be customer. Okay, so you would have various instances of customer, and what things might be subordinate to the customer record? Well, they have first names, they have last names, they have addresses, they have phone numbers, etc. Right? So this is how you can kind of create an object or a data thing that contains more than one piece of information. All of the stuff we've done up until now has been, you know, an integer or a character or a float or something, but it's always been a single piece of data. Maybe the exception to that would be strings or arrays, because those are, you know, sort of a group of these things. Okay, so the Kernighan and Ritchie, right, the book, right, starts with an example of a struct, okay, just to kind of get us going. And this is certainly a perfectly good one to use, which is, what about if we were defining like points in geometry? Okay, they have coordinates. Okay, and so, and let's just say, for sake of simplicity, restrict our attention to doing things in 2 dimensions. So if I wanted to define a struct that was a point, okay, then what I have to define is sort of like I have to define a function outside of main. I have to define what is a point struct by its nature, okay? And so here the syntax is struct, because I'm creating a struct. What am I going to call this particular kind of structure? I'm going to call it a point. That could be whatever name I wanted. Okay, and then what things go inside a point, right? So what pieces of information do I need to specify a point? Yeah, x coordinate, y coordinate, maybe a z coordinate if we're doing 3 dimensions, but we'll just do 2 for the sake of simplicity. Okay, and let's just say that we have an x and a y coordinate, and I'm going to define these as doubles, double precision floating point, so that like there's going to be there might be decimals and stuff, right? And I want to include that possibility. So we'll just go ahead and define them as doubles. And then this is something that's going to annoy you guys. With the struct definition, you have to have a semicolon after the curly brace. You don't have to do that with functions. I know that's kind of annoying, but yeah, you just have to have it there. So don't forget it, okay? So what I have defined here, I have not defined a particular point. I have just defined this abstract category of things called point, and I could have this point versus that point versus some other point, okay? Good? So then if I want to actually create an instance of this point, then I can do that down in my main, for example. Let me go ahead and put that in there. And so what I would say is struct point, that's the kind of thing I'm creating. And then what is the name of the particular point that I want to make first? Well, that's up to me. What's a logical choice? Well, I need to be careful about my lettering here. Let me call it point 1. Okay. So struct point 1 declares that I am creating a particular instance of the struct, the point struct, and the name of said point struct is PT1, just whatever, okay? Now, so I've declared the existence of a particular struct. Have I initialized its value? No, okay? I could do that right now by saying this equals and then curly brace, and then the stuff that goes within it. Okay. Now I'm not going to do that this way. What I'm going to do is a different way. Okay. So point one has what things within it? It has an x and a y. And the way that I get to the x coordinate is pt1 dot x. Okay, so that says, all right, from the point pt1, access me the x thing within it. Okay, and then let's just make up something for this. Okay, some number, it doesn't really matter. And for the y coordinate, let's make up some other number, whatever. Okay, and now the point is completely initialized, right? Not only does it have does it exist in memory, but I've actually given its x and its y coordinates some sort of data. Okay, all right. Does that make sense? Yeah. All right. So now that we've done this, what could we do with this point? I've created it, but like, great, I've created a point. Now what? Okay, graphing it, yeah, we could. We'd have to talk about like how you do graphics and stuff, and that's not as easy in C as it is in Python. Because in Python, right, you just import some magic library that does all kinds of crap for you, and that's the end of it. Okay, so yeah, we could graph it theoretically, but what other things could we do? Like, well, if I can have one point, can I have two? Could I then compute like the distance between them and all that sort of fun stuff? Yeah. Okay. So, yeah, so let's compute the distance between 2 points. Sound fun? Okay, so in order to do that, I need another point. And this one, let me go and define um, this way. Give me some other numbers. Okay, and 4. Okay. Now, to be clear, when we say 7 and 4 here, what is the 7 and what is the 4? Yes, okay, but 7 is what kind of number here? Is it? How did I define my struct? As a double, okay? So even though I've typed just 7, that really is 7.0, meaning it's a double, it's a floating point number, not 7 as an integer, okay? And that's important, okay? Okay, so I could instantiate each point in either of the two methods, okay? Which one is better? Well, I don't know. That's kind of a eye of the beholder kind of thing. The first one is certainly more explicit. The second one's more compact, right? Does it really make a difference? Yeah, just depends on your preference. Okay, so sound good? So if I want to compute the distance between these 2 points, let's make a function that does that. Okay, and for this function to work, what kind of data do I need to pass it? Hmm? Well, can I pass the actual structure in the same way that could I pass a string to a function? Okay, that's almost a trick question. And so can I pass an integer to a function? Can I pass a floating point number to a function? Sure. Can I pass an array or a string to a function? Not by value, but what can I do? I can pass it by reference, which is to say using a pointer. Okay. Now, the way, so let's go back to the strings function code. So here, right? Uh, so I pulled up our uppercaseify code from before. What did I pass uppercaseify here? Doesn't it look like I passed it a string? Because I said, all right, it's going to take in an input string of some length, right? That's a string. It looks like I'm passing it a string, but am I really passing it a string? No, I'm really passing it a pointer to a string, okay? And this is why this version, so remember we wrote uppercase of I version 2 that did the exact same thing, but we just defined it as explicitly accepting a pointer instead of sort of accepting the name of a string. So what did Kernighan and Ritchie say that which is preferred? This syntax for up like we did with uppercase of I version 2, or this syntax for uppercase of I version 1? Which is preferred according to Kernighan and Ritchie? The second one, because it makes explicit that we're passing a pointer. However, the first one, is the first one easier to read and understand? Very much so, okay? Which is why the first one is syntactically valid, okay? Okay, so my point here is when with functions, and maybe you guys think I sound like a broken record here, okay, and I probably do. You can't pass anything but numbers as value. You can only pass pointers to them or references to them, okay? Even if it doesn't look like that's what you're doing. Okay, so we've got sort of the same issue here with how are we going to do a function that accepts structs, okay, or rather, sorry, structs and functions, okay. So do we see kind of what the issue is here, what we have to kind of worry about? Okay, so let's think about the distance formula. Okay, so what kind of data should the distance function return? A double, okay? And because if I've got 2 points and I compute their distance, well, the distance is a number, right? What kind of number? Well, since our original numbers were all doubles, then let's just keep everything as doubles, and we don't have to do any type conversions, okay? What do we want to call our function? Distance sounds good. What data needs to come into this function? So what am I computing the distance between? 2 points, okay? And so what I'm going to do is I'm going to say struct point pt1 and struct point pt2, okay? So those are the 2 points that are coming in. And you know what, actually, for sake of clarity, let me do this. Let me call this one PTA and this PTB. Okay, why did I change it? What's maybe the advantage of me changing it? I'm not using PT1 in 2 different ways. Okay, maybe that's confusing, maybe it isn't. Okay, so within this function, the 2 points that we're working with have temporary names, PTA and PTB. So if I had 3,000 points in my program in memory, then, and I wanted to know the distances between lots of different ones, I would say, okay, distance function, I'm going to give you 0.37 and 0.1832, compute the distance. Okay, and then within the function, point A and point B are the 2 points that I'm currently considering, whatever they are. Okay, okay, so got that. What is the distance formula? Yeah, well, what's the distance formula? That's the slope formula. Okay. It's the square root of something, okay? So it's the square root of, and actually we need to do f square root because it's a floating point that we're dealing with, not an integer, okay? So what we need to do is and let me actually build this up. Okay, I need to take the differences of the x coordinate and the differences of the y coordinate. What do I need to then do to each of those? Square them, okay? So I'll just say temp1 equals temp1 times temp1, and temp2 equals temp2 times temp2. So that squares them. Okay, and then what do I need to square root here? Temp1 plus temp2, the sum. Okay, and this would be the actual answer. Okay, so what is the distance formula? The square, well, what is Pythagoras' theorem, right? The square root of the sum of the squares. And what are the legs of the two triangles? The legs are the distance of the x, or sorry, the difference of the x coordinate and the difference of the y coordinates. Okay. Okay, so that's just math, right? But it's some formula that we could look up. Okay, so is that okay? What do we need to return then? What's the answer? The dist, okay? So I'll return dist. Okay, so I've now defined a function that's going to accept basically pointers to two structs and then get their x and y coordinates and then compute the distance. Okay, sound good? All right, so now we've already defined 2 points. So let's say here, double dist equals distance of between what and what? PT1 and PT2. Okay, those are the 2 particular points that we wanted to deal with, right? Okay, and now let's print it. Okay, so the distance between the points is, what kind of numeric data do I want to output here? A float, which is really a double, okay? And it will, and what number is it that I want to output? Whatever the result of dist is, this computation here. Okay? All right, so that makes sense? All right, so let's compile it and see, hopefully make sure it all works and that I haven't screwed anything up. Oh, right. Okay. Sorry. I think we need, I think it's in math.h. Okay. I don't remember where f square root is defined. Hang on one second. Because %d is for sorry, I don't want f square root, I want just square root. So say the question again, sorry. %d is for integers, right? So %d and %i are both ways of doing an integer print, but we're not printing an integer, we're printing a floating point number. Okay, so yeah, this is sort of the confusing thing. When we say d and we mean decimal, that's not really what we mean, like in the sense of like there's a dot and some digits. We just mean an integer. I think there's a historical reason why there's that distinction, even though it doesn't really matter. But I'm not sure what it is. Okay, so my bad. It's just no. Where? Dang it! I thought I square root. Okay, hold on. Did I include math.h or did I get rid of that? I did. Okay. Oops. Undefined reference to square root. Did include math.h, didn't I? Okay, did I mistype it? Square root? No, that's okay. All right, so why isn't this working? Well, this is kind of a showstopper, isn't it? Okay, so I did include okay, I'm forgetting something here, which is because it should just math.h should have it. Okay, hold on, let me math.h. Okay, I don't know why this isn't working, guys, because we're using the math.h, which should give us the square root function. All right, well, let's move on. What should happen here? It should return whatever the value is, okay? And we need to have math.h, so I'm not understanding why it's throwing a, huh? I did save it. That's the first thing I checked, was to make sure that I actually saved the code to have, and like I said, I was pretty sure it was math.h that we needed. And I did type math correctly, didn't I? Okay, I'll figure out what I'm doing wrong. It's probably something really stupid, right? Because if I, like, let me just make a stupid little test thing, right? So let me do, right? So if I do this, what should happen? See, okay, that worked. Okay, so then what did I forget here? Oops. Oh, I see what you mean. So like this. Okay, good idea. No. Okay. Um, you know what? Just for sake of, let me do this. Let me, let me, no, it's not on yours. What? Are you like remotely logged in? Oh, okay. Well, that may change it because it may be using it. So when you type GCC, it's not actually using GCC. It's using Clang, which is what Mac OS uses as a compiler. Um, okay. So just to move this along, right? I'm just going to return the sum of the squares, and then I'll actually do the square rooting out here. So instead of dist, I'll do square root of dist. And if that works, then I'm going to like throw something out of a window. Okay, this makes no sense whatsoever. You know what? I'm going to put it first. Sometimes that actually matters, believe it or not. No. Yeah. Okay, let's just ignore the square root part for right this instance. Because like that's not the point, right? The point is how we're passing stuff back and forth, and I'll figure out why what's going wrong later. Okay, so all right, so we get here the distance between the points. Well, really, it's the square of the distance because I haven't square rooted the answer, and we got 16.0. Okay, that was sort of coincidence that the numbers that you and me happened to pick were nice Pythagorean, right? The distance was a whole number. It didn't have to end up that way, okay, but it did. Okay, so good. Other than the square root issue, which I'll figure out. Yeah. Okay. So there's some reason why it's not working, and I just don't remember what it is. I think you have to like pass GCC um, an extra argument. I'm starting to remember back in the day having to do something, but I'll figure that out and let you guys know. Um, okay. So yeah, but the square root thing, right? That's not important. What's important is, and actually, you know what? Now that I say that, I do remember. Patrick, didn't we have this problem at some point in the past where we had to pass something to the compiler to tell it to actually use the math? Um, Let me go back to last year and see because I remember we ran into this and I just don't remember what we did to fix it. Um, okay, so fall of what was last? This is fall of 22, correct? So fall of 21 was last year. Okay, got it. Let me look back at the Canvas page and see if I can find it. Okay, what was the Structs assignment last time? No, not that one. Oh, that's right. Okay. Here it is. Okay. So let me put everything back the way I had it. Okay, the square root there and the distance there. Okay, so you have to add the dash lowercase l and lowercase m flags when you compile. Okay, and now it works. Except I saved it, but double distance, the square root of those two things, return temp1. So it should have output wait a minute, it should have been 4, not 16. Oh, it's because I forgot to change this. Sorry. There we go. I was returning the wrong thing. There we go. Okay. All right. So what did I have to do for the math part is I had to add this flag to GCC when I was compiling of dash lowercase l dash and then the m. So lowercase l m. For it to correctly use the square root thing. So that's weird, but sorry. Huh? So I'm not sure right off the top of my head. I remember figuring out why last time. So part of it, I think, and let me I'll double check this after class, is if we go back to the history of C, right? When did the C programming language come into existence? 1832. Yes, Caleb Mills knelt in the snow and he's like, there will be computers and they will have this language called C. Okay. No, it's not that old. It was 1970s. Okay. And at the time, okay, most computers did not have the ability to do hardware square roots. Okay, they could do software square root. Okay, so what's the difference between hardware and software when it comes to this? Hmm? Well, okay, yeah, but like, how do you do addition of two numbers? Right? Is there a circuit inside the processor that actually does the addition, or is there some sort of piece of code that runs that actually computes the addition? It's the former, right? There's an actual circuit inside the logic unit that computes sums, can also do differences, okay? If we go back to mini and microcomputers of the day, okay, so for example, my Commodore, right, in all of its 8-bit glory, it did not have hardware square roots. It could do hardware addition and hardware subtraction. That was it. Well, and shifting, okay? But it couldn't do hardware multiplication or hardware division. So if you wanted to do multiplication, you had to write a program that did that, okay, or a little subroutine or a function, okay? Similarly, if you wanted to do a square root, you'd have to write some sort of function, okay? So back in the day, there was no hardware square root. You had to have software to do it, okay? Nowadays, though, the Pi and the processors that's in there, and of course, pretty much any other modern computer, do have hardware square root units and hardware lots of other things. Okay. And my memory is that the LM is basically telling the compiler, hey, bro, my hardware can do this. So you don't have to use the software routine. You can use the hardware function, which is faster. Okay. Much faster, like orders of magnitude faster. Okay. So anyway, now that we've got that sorted out, no big deal. Okay, so let's just kind of recap what have we done thus far, right? We've defined what a struct is and made an example struct that had within it 2 points, okay? Or, sorry, 2 coordinates of a single point, okay? Sound good? Yeah? What else could we do? And we also wrote this distance function. Does the peanut gallery have something I'd like to add? No? Okay. Well, that sucks. Take it up with campus services. Well, I'm very sorry, but this is in the department of not my problem. Okay. Huh? Yeah. No, I didn't know that. I've been using 1832 completely at random for the last 11 years of teaching. No, it has nothing to do with computers. Kids these days. Okay, so the distance here was just an example function that could involve using data from structs. Could have come up with any other function that I wanted. So if I can define a struct as a point, or a point struct, could I define other structs that are also geometric objects? Like what, for example? What might be a thing that has multiple points? Triangles. Okay, what did you say, Patrick? A rhombus. Okay. Now, the thing with the rhombus actually is, how do you know that it's actually a rhombus, right? Can I just throw any 4 points together and have a rhombus? Not necessarily, right? Whereas, can I throw any 3 points together and have a triangle? Technically, yes. Now, it might be a stupid triangle, like that doesn't actually enclose any area, but it's still technically a triangle. Yeah. Can I struct structs? Yeah. Okay. Now I know what you're about to ask. Can I make a struct that contains within it other structs? Oh, um, so could I struct 2 points together and then figure out the third point? Well, okay. But there's infinitely many solutions to that, right? So basically, like you're asking, can we do trigonometry? Yeah, of course. Okay. So um, what? But in order to do that, we need to have an object called a triangle, right? That we can work with. Well, what is a triangle? How could we define that? We could define it as a thing that has 3 points, right? We could also define it instead as like 3 sides, okay, 3 lengths. What might be the best way to do this here, especially given that we've already constructed a point type? Well, let's make it as a triple of points. Okay, so does that make sense? Okay, so let's come up here, and after we've defined our struct point, let's make a struct triangle. Okay, and what stuff is going to go inside of a triangle? 3 points, which are themselves structs. We're structing structs. Yes. Okay. So it's structception, struct all the way down. Okay. So when I've done this, what have I said? The triangle struct is a thing that contains within it what? 3 points. Well, those points are themselves structs that contain their x and their y coordinates. Okay, whatever those happen to be. Okay, so I can totally do structs of structs. And you can, I mean, obviously you don't want to like nest this stuff too much because then it just gets confusing, but you could do that, right? You can nest it basically as much as seems reasonable. Okay, so if I can define a triangle as a triple of points, well, what interesting things might I want to do with that triangle other than graphing it, say, just because that gets us into graphing territory and I don't want to go there. Well, what can we do? If we got a triangle, what kind of math questions might we ask about said triangle? Okay, we could find angles, right? We could find the lengths of the sides. Okay, what type of triangle, meaning is it like scalene or isosceles or something? Okay, what else? What else could we what questions could we ask about triangles? We could ask its area, we could ask its perimeter, we could do all of those kinds of computations, okay? Okay, so let's just use the area and the perimeter as good examples, okay, for right this instance. Well, so how do we compute the perimeter of a triangle? The length of all 3 sides added together, okay? Now, fortunately, do we know how to find the length of a side? Yes, we already wrote a function to do that, the distance formula, okay? So we just have to do that 3 times. That's not so rough, okay? What about the area? How do you compute the area of a triangle? Okay, base times height or length times width over 2. Yes? But do we know what the length and the width are? Necessarily. Okay, so we have to do something else. And for that, let me get out my iPad so I can write something on that screen. Okay, so we're in math territory now is the fun part, right? Okay, so okay, can we all see the iPad screen? And make sure we're still capturing it. Okay, so if I have a triangle, something like that, and I want to know the area of it, let me just call the points A, B, and C just for sake of example, and let me call the legs B, A, and C. And the convention that we happen to use a lot in trigonometry is capital letters for the points, lowercase letters for sides. Okay, whatever. So how do I compute the area of this thing? Well, if I happen to know that it's a right triangle or I know its base and its height, then I can just do base times height over 2, right? What about if I don't know that? What about if all I know is the 3 sides and I don't know what type of triangle it is? How do I compute the area? That's only would work if the angle at C is right. Anybody heard of Heron's formula? Ah, Patrick, brilliant. Thank you for that suggestion. Okay, so I'm going to define the quantity S is A plus B plus C over 2. This is called the semi-perimeter. That would help if I could write today. Okay, so the perimeter is A plus B plus C, right? The semi-perimeter is merely half of that, hence semi. Okay, so I'm going to define that quantity, and then the area turns out to be the square root of S times S minus A times S minus B times S minus C. Did you guys learn that in high school? But you see it, now that you see it, you're like, oh, I remember seeing that at some point. No, you've never seen that in your life? Oh, sad panda. Okay. Um, did Aaron have any friends? Well, the question mark was rhetorical, okay, for you, right? So, um, okay, so yeah, heron, ancient Greek. No, seriously, no. You guys never learned this in high school? Oh, you're making me a very sad panda. Yeah, well, clearly. Okay. All right. So, if you didn't know that hitherto for, you do now. Bam, there's the formula. Okay. Okay, so what four pieces of information do we need to do this computation? We need to know A, B, and C, and we need to know S. Okay. So, how do we get A, B, and C? What are those quantities in terms of my diagram? They're the lengths of the three sides, right? Okay, so how do we compute the lengths? We need to pass our distance function 2 points, right? This pair, and this pair, okay? And then if I add those three numbers up, then I know the perimeter. And can I take that divided by 2? Sure, okay? All right, so let's go back to pi and actually program this sucker. Okay, so let's come back up to here. Okay, I need a third point, right? So far we have 2 points, but I need a third one in order for us to have a triangle. Any suggestions? Let's do a negative, just so it's, 2. Okay, fine. All right, so -1 comma 2. So those are our 3 points. And just for cleanliness, do you guys mind if I do that? Okay. Just to make it a little bit cleaner to read. That's the only reason I did that. Okay. Now, I also need to define the triangle structure. Okay. So struct triangle, and let me call it my tri. And what is it built out of? Point 1, point 2, and point 3. Right? Those are its 3 points. Okay. All right, good. Okay, so I want to then write, we've already got a distance formula function, right? So if I wanted to write a function that computes the area, it will return a double. What kind of information does it need to take in? It needs to take in a triangle. Okay, and let me call it temp tri for within this function. Okay. All right, so what computation does the area function need to do? Well, what's the first thing we need to do? We need to compute the length of all 3 sides, yes? Okay, so let's call double A equal distance between temp tri dot what? Dot A and dot B, or dot point B, right? Okay, similarly, what do I need to do for the two other distances. Yeah, so B is from, well, okay, technically, here, let me do it in the correct order. Oops. Okay, so C goes from A to B goes from C to A, and A goes from B to C, right? That way it matches what I had in my diagram that I sketched out, okay? All right, so those are the distances, and then what's the other quantity we need? We need the semi-perimeter, which was what? Yeah, the sum, which is the perimeter, all over 2, okay? And then, what's the area? Okay, I can't call the answer area because I've already called the function that, and I can't use the same thing twice, right? So let's call it this. So what is the answer? It's the square root of s times s minus a times s minus b times s minus c, parentheses close. Okay, so that line is Heron's formula. Okay, good. Okay, and what am I returning? What should this function return? The answer, okay, or ants, the variable. That's just what I chose to call it. Okay, so return ants. Okay, all right. So now I have 3 points, and I've created the triangle out of them. Okay, and let me delete this. And then, so the area of the triangle is something. And what do I need here? Right? I'm passing it the triangle my try. Okay? And then this function returns the new number, my area. And there we go. Okay, so does that make sense? All right, so let's hope that it works. Okay. Oh, and I forgot to put a space there just to make it readable. Okay, so the area of the triangle is 4.0. Does that make sense? Well, let's think about it. Look at the first 2 points, 3 comma 4 and 7 comma 4. What's the distance between those? 4, clearly, right? Because they have the same y coordinate, so they're horizontal, okay? And then the other point, -1 comma 2, so we happen to have here, we do know the base and the height. What's the base? 4. What's the height? 2. And what's base times height over 2? 4. Okay, so by coincidence, the 3 points that we picked happen to be make the area like a nice whole number. Okay, but if I changed one of these to something like this, oh well, duh. No, changing that one's not going to do it. It's I wanted to do something like this, so that it's no longer a base times height over 2 thing. Well, did I save it? Oh, actually, this is interesting. Do that, say. Okay. Um, that was actually guaranteed to happen because of math. So the coordinates that I've picked here, right? All of the coordinates are integers, yeah? And there's this thing called Pix Theorem, yeah? All right, so let's put in some more horrible numbers, shall we? Okay, that's better. Thank you. Okay, so it turns out there's a theorem from geometry that if your triangle, if all three of its points have integer coordinates, then its area is a multiple of a half. It's called Pix theorem. Um, so, what? No, it's just geometry, right? So it's because I was picking bad numbers that it looked like I was always getting a whole number answer, but that was just coincidence. Okay. Okay, so great, we got this thing. All right, now, what would we need in order to compute, say, well, we've already computed the perimeter, right, as part of doing the area computation. Um, what other kind of interesting things could we do with a triangle object? Yes, okay, but what would be required? So Patrick's suggestion is, could we make a pyramid or like put multiple triangles together? Uh, we could do that, but then we would have to add a third point, or sorry, a third coordinate to all the points so that the object could live in 3 dimensions. Okay. But otherwise, yeah, we could totally do that. We just have to add a z coordinate. Okay, no big deal. And if I created, say, a pyramid, what would a pyramid look like? Or what would a pyramid be built out of? 4 triangles, perhaps, okay, to make it a tetrahedron. Uh, and then a pyramid, like in the Egyptian sense, what is that? Square base, 4 triangles, all of which happen to be the same, like in they're congruent to each other. Okay, so actually, would you need? How could you define a pyramid? Would be enough to specify the square, the base, and the height of it? Would that be sufficient information if you're building it sort of Egyptian style? Yeah. Okay. Yeah. So we can define solid objects, and the second we do that, what kind of computations might be interesting? So yeah. Okay. So 3D area would be was what do we mean when we say 3D area? Volume. Okay. Or the surface area. One of the two. Okay. The volume would be something in cubic units, whatever the units are, and the surface area would be something in square units, whatever the units are, again. Okay. But we could compute all of that stuff, right? So, for example, if we defined a tetrahedron as a struct of 4 points, or sorry, 4 triangles, each of which is defined as a bunch of 3 points, could we compute the surface area of that? Sure. Okay. Um, now, if we go back to the triangle thing, you guys suggested we could also compute angles. Yeah. Um, how would I compute the angles in between uh, using? So let me go back to the iPad for a second. Okay. How would I compute, for example, the angle at A in terms of the sides? So if I know all 3 sides, how do I get the angles? Okay, but SOHCAHTOA only works if you have a right triangle. Otherwise, you have to use the law of cosines. which is c squared equals a squared plus b squared minus 2ab cosine of c, okay? Or the law of sines, which is that sine of a over a equals sine of b over b equals sine of c over c, okay? So do you guys remember seeing those in high school? Kiani? No? Yeah. Okay. So basically you have to do trigonometry. Okay. Now, this begs the question then, in the same way that we needed to be able to use the square root function, are there trig functions that are in C that we can access, like cosine and sine? Yes. Okay. But actually it's a little bit worse. With the law of cosines, do I need to know what the cosine of an angle is? No, because I don't know the angle, right? What I want to do is actually solve that equation to find C in terms of everything else. So I don't want to take the cosine, but rather the arc cosine, right? So I need to use an inverse trig function, which is even more fun. No? Yeah. So like it'd be a perfect like clickbait thumbnail for the YouTube. Like, professor goes crazy with math, right? No? Okay. Could work. Okay. Um, okay. So yeah, so I'll come up with something interesting for you guys to do with structs of structs of structs of structs. Okay. Well, okay, and maybe I'll come up with two versions. The one for those of you who are not afraid of math, and the one for those of you who are afraid of math. Okay. Or maybe I could just tell you to man up and do it. And if you don't want to do math, there's a school 30 miles south of here that might be accepting transfer applications. Yeah? What do you think about that? Harsh? Yeah. Well, sometimes you guys need a little bit of tough love. All right, so let's go back to the pie. All right, so the last thing I wanted to hit, at least today, was this business with the flush function that I posted on Canvas about. So let me just go to my announcement there. Just so that we're all clear. And of course. And it's going to do the stupid thing with the authenticator. Because we can't have nice things. Oops. Okay, so I just wanted to make sure that you guys were all clear on this note. So let me copy and paste this and put it into here. So I'll just put it up before the main. Okay, so this is a piece of code that Dr. McCartan Lim wrote many years ago. But essentially, there's an issue with when you use scanf or getcar, okay, or some of you guys have been using fgets, okay. All of these things use input buffers, and sometimes the buffer still has stuff in it when you try to go back and get another character or accept more input. And you've got to flush the buffer, okay? So this function called flush basically just sits there and says, while there's still stuff in the buffer, just keep looping until finally the buffer is empty. Okay, that's all it does. Okay, and so if you're having issues where, like, let's say you're accepting multiple user inputs one after another, and the first one works, but then the second one doesn't even seem to let you be typing anything, just add this flush function in, and then right after you call scanf or getChar or anything that's taking input, just use the flush function. Okay, and that will 99 times out of 100 solve your problem. Okay, yeah. So that little piece of code, I put it up on Canvas. You just have to add it in someplace, and then you would call it by just saying flush with parentheses and nothing in it because it doesn't accept any input. Okay. So yeah, so if you're having issues with the input, like scanf and stuff, 99 times out of 100, that'll fix things. This is kind of an annoying issue. Okay. So this, one of the things I would like you guys to do as part of the Structs assignment, okay, is you see how we've used the dots here to access a member, if you will, of a structure? There's also a pointer way of doing that, okay, which looks a little bit differently, or looks a little bit different, but kind of means the same thing. All right, so that is on basically on pages 131 and 132, which is, okay, about, the thing with C. If I can have an object, any type of thing, a number, a struct, a string, whatever. If I can have a thing, what else can I have? I can have a pointer to that thing, right? So what do pointers look like for structs, right? How do you deal with a pointer to a struct? That's what those couple of quick pages are about. Okay, but let me also then, sorry, let me go here. I'm going to print this, and okay. So, what I had it do was, well, if I can have my try, then what's ampersand my try? It's the address of it. It's a pointer to it, okay? And the reason I wanted to do that is so that I can do the following. Well, let me go out to a full terminal because it'll be easier to read. Okay, I want to add a breakpoint at line 53. Okay, so where did it just say that the structure was located in memory? 7 FFFFF EF48. Okay, whatever. So let's look at memory there. What was it? 7 FFFFF EF48. Okay, so if I look at this, it's not going to look comprehensible in the same way that looking at strings in memory was, okay? And the reason is, what kind of data built up the triangle? What was the triangle made of? 3 points, each of which were a pair of doubles, okay? So Double precision floating point numbers are encoded according to a particular scheme, right? Namely IEEE 754. And so if I look here in memory, is it obvious how any of these numbers are what you think they are? Right? So for example, I defined one of the numbers to be 3.14, just, picked it kind of out of random. Is it obvious where 3.14 is here? No, okay, because the numbers are encoded in as doubles, and that doesn't mean, so doubles, you can't just look at the memory and read them off, okay? We'd have to decode these and see what we get. Okay, but does it at least look like we have sort of the right number of numbers? And also, how many of these do we need to define a 64-bit thing? Right, so a double is a 64-bit thing, correct? So how many of these 64 bits is how many bytes? It's 4 bytes, right? Huh? Yeah, so 64 bits is 8 bytes, right? Because 8 bits make up a byte, and 8 times 8 is 64. Okay, each one of these chunks is 4 bytes. So 2 of these chunks put together is a 64-bit number. And in order to look at this, 51EB, 85, blah, 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 we would have to know the encoding scheme for IEEE 754, which we'll talk about, okay? But that I think will come later. Okay, so the last thing, just kind of preview of coming attractions for where we're going next is okay. So next time we're going to start with assembly, Thursday. Right, today's Tuesday. We also have class on Thursday. So we're going to look at what the heck all of this crap means. Okay. Oh, doesn't this look wonderful? Right. Okay. Now, granted, this is sort of a ridiculously long uh, program that we've written. Okay, but we're going to start writing things in bare assembly, okay, by hand instead of in C. Okay, and we'll use C as sort of a glue to help us get started, but yeah. Yes. No. Well, you can, but yeah. No. So, yeah, I mean, if you want to use Python to kind of figure out how to do something and then figure out how to translate it into C, that's my guess. But if I tell you to turn in assembly and you give me Python, what am I going to do? Return it back to you. If you give me lambda calculus, I will send you across the hall. Okay. All right. See you guys Thursday.